Good evening. If you're not interested in the motivational babble, feel free to skip ahead to the next chapter. Moreover, if you're currently playing Turing Complete and don't want any spoilers for the levels Full Adder and Adding Bytes, you may also want to skip ahead. Otherwise, let me explain to you the motivation for this video's subject. When tasked with building a binary full adder, you might come up with something like this. These AND, NOR combinations are XOR gates. This circuit XORs the summand bits and the input carry together to get a 1-bit sum. It also taps into the AND parts of these XOR circuits and ORs them together to check for the carry output. For now, understanding the what is sufficient. The why will become apparent later. The next level tasks you with building an 8-bit wide adder. The naive and most straightforward approach to this is just chaining 8 full adders. As you can see, the carry output of one adder connects to the carry input of the next. This approach is called a ripple carry, because the carry ripples, so to speak, through the entire byte. This works, but if you look at the stats, it has a lot of delay. For reference, there is an achievement for this game and this level that tasks you with building a byte adder with a delay of 35 or less. 64 misses that mark quite significantly. What's the culprit? Well, if we enable the delay view, the problem becomes immediately apparent. Every adder adds 8 delay points, and because components won't function until all their inputs are ready, every subsequent adder has to wait for all the preceding ones. But wait a minute. If you look at the adder's inputs, the adders have to wait for their carry inputs, but the summonds are always immediately available. Could we make use of that? Well, I wouldn't be entertaining that question if the answer were no, would I? So let us examine the second approach. Previously, we did everything in series, but now we do all the half additions of the two summonds simultaneously. This allows the first half of every bit addition to be processed while the carry input is getting ready. Or in other words, once an adder has to wait for its input carry, said carry input has already been half processed, you see here, half of that, in the previous adder. The result is that the carry delay per bit is shorter, reducing the cumulative delay. And reduce the delay it does, almost halving the delay score from the previous 64 to only 36. However, this still exceeds the delay limit for the achievement by 1 point. Bummer. If we examine the delay view once more, we unsurprisingly find that the carry is still the main contributor to this delay. See, here for instance. It's less than before, but it's still there. The problem is clearly that we still have to perform an entire full addition of 2 bits to determine the carry input for the next. But then how else are we supposed to know the carry? I mean, we can't just see into the view. Yes, we can. The 6502 is able to determine the carry output of any given bit of an addition without having to consider the addition result of the previous bits. To do this, it employs a technique called carry lookahead. If you already know what the terms generate, propagate, and kill mean in this context, then you may as well skip ahead to the next chapter. Otherwise, let me give you a quick rundown of the logic behind carry lookahead. Here we have a truth table showing the bit sum and carry output for all different combinations of summoned bits A and B, as well as the carry input bit C. Perhaps if we study this, we can determine some heuristics about carry behavior. If we focus on all the columns where the carry output is 0 and inspect the input bits, we see that there is always at most one enabled input. Here we have 0, here we have only A, here we have only B, and here we have only C. Conversely, if we focus on all the columns where the carry output is 1 and inspect the input bits, we see that there are always at least 2 enabled inputs. Look here, A and B, here A and C, here B and C, and here A, B and C. The logical conclusion then is that the carry output is set if and only if at least 2 of the 3 input bits are set. Alright, nice trivia, but how does that help us? Well, it just so happens that we always have 2 of the 3 input bits available from the start, the summand bits A and B. By looking at them, maybe we can come up with some heuristics for what the carry output of any given bit will be. Let's consider just the 2 summand bits, disregarding the carry. In the leftmost bit column, both A and B are 0. Now, if we already know that 2 of our 3 input bits are 0, then there is no way for at least 2 to be set. Therefore, the carry output can never be set. If the carry input, not displayed here, were set, any previous carry propagation would be terminated in this bit. Thus, this condition is endearingly named kill. Conversely, in the rightmost column, both A and B are 1. We therefore already know that the condition for a set carry output is fulfilled, meaning the carry output is set regardless of the input carry. We basically generate a new carry from the summand. Lastly, in the 2 center columns, exactly one of the 2 summand bits is set. If the carry input is also set, we have the 2 necessary set inputs for a set carry output. Otherwise, there is only one set input and therefore no carry output. In effect, this means that the carry input propagates to the output. By checking for these 3 carry conditions, we can essentially bypass the addition circuitry altogether and determine the carry out of each bit separately, in parallel to the addition. But how do we check for these conditions in hardware? Why, we just need to find logic gates that output a logical 1 if and only if their inputs match the appropriate A-B combination. For the kill signal, we need a logic gate that will output 1 if and only if both inputs are 0. This is the behavior of the NOR gate. Conversely, for the generate signal, we need a logic gate that will output 1 if and only if both inputs are 1. This is of course how the AND gate behaves. Lastly, for the propagate signal, we need a logic gate that will output 1 if and only if exactly one of its inputs is 1. This can be achieved with an XOR gate. Alright, equipped with theory, let us dive into practice. This is the ALU of an almost exact 6502 replica I may or may not be working on. Now, originally I was going to spend what would probably have been an hour iterating over a textbook example of a carry circuit, optimizing it to match this, explaining the reasoning behind it all, and proving to you mathematically why it works. But then I thought, let's not put people to sleep. So instead, we'll just explore and accept how this particular circuit works, while leaving the reasoning largely aside, maybe for another video. It's a bit much to take in with all the components and wires going everywhere, but conveniently, to the point of appearing predetermined, someone has colored the carry line turquoise. The part we are interested in is found by following the line downwards. The branch to the side goes to what appears to be the decimal carry circuit, but that is beyond the scope of this video and my understanding. Anyways, if we follow the line down here, we quickly see some wires with familiar terms: kill, generate, and propgen? Hold on a minute. Where is the propagate line? Why is this generate line inverted? And what even is a NAND? To answer these questions, let's view the circuit in isolation. Now, firstly, one thing you should know is that the carry input is actually inverted, hence the preceding slash. Here. And this is true for every even-numbered bit. This means that the carry line into bit 0, 2, 4, and 6, as well as the carry out of bit 7, is 1 if there is no carry. So right now this is set to no carry, and it would be 0 if there is 1. For the odd-numbered bits, the carry inputs line actually behaves intuitively as you would expect. So the carry into odd-numbered bits, like into bit 1 here, see 1 is the carry into bit 1, is off if there is no carry and on if there is a carry. So please keep that in mind, that the carry input is inverted for every even-numbered bit. Next, about the propgen line. It's probably fairly obvious what's going on, but I'll quickly explain the logic behind it. So we've got these 3 possible carry states: kill, propagate, and generate. We know them to be mutually exclusive, at least for the sake of argument, and that one must always be active. Now, if there is no kill signal, well, then we know that there must be a propagate or generate signal. We don't know which of the two it is, so in effect this is a sort of fuzzy double signal, if you will, but it turns out that this will be good enough for our purposes. And it's a bit cheaper to implement in terms of circuitry, hence why they did it that way. Lastly, before we analyze the logic flow, I will actually slightly rearrange this circuit to make it more straightforward to understand. So, we will begin by replacing this NAND gate with its logical equivalent. Following De Morgan's laws, there's a page in the game manual, of an OR with both inputs inverted. So we'll put that here, then both inputs will be inverted, and I'll also label them just to make this easier to understand. So this would just be generate, no longer inverted. This can go now. By the way, this is ironically actually closer to how it is depicted in the original logic diagram. It's also depicted as an OR with both inputs inverted, but it's using a shorthand that cannot be replicated in Turing Complete. So in the original logic diagram they don't have these inverters as explicit components. Again, there's an input, a shorthand at the inputs of the OR gate. And I wanted to stay as visually close to the original diagram as possible, so I replaced it with the logical equivalent of a NAND gate, but I'm undecided if I mightn't leave it like this after all. But anyways, So this here, this OR with both inputs inverted, is the equivalent to the NAND gate we had before, but I think it should then be easier to tell what's going on. And then if we go down here, we'll actually also replace this NOR with an OR that has its output inverted. And this is mainly so that this output actually, this component output actually behaves intuitively correctly, so that it shows the carry state before it's being inverted again for the next even numbered bit. Okay. Anyways, with these alterations, the logic flow should now be far easier to follow. Especially now that these input bits have been inverted. The logic for the even bits is actually slightly more complicated in my opinion, but no longer by much, so let's just dive in. We'll go through it backwards actually, because once again I think that makes it easier to understand. So we'll start at this AND gate that actually comes at the end. So, first of all, we've got this bottom input of this AND gate being fed with the propagation signal. And if that is off, well then we also know that implicitly know that we are in the kill state. And so we can actually ignore any of this logic here, this OR with its inputs inverted, we can just ignore that, because if we're in the kill state, we're never gonna have an output carry, and so, well, that's that. The kill state takes precedence, it overrides anything else. But if we are not in the kill state, well then we may be in the propagate or generate state. And now, to know if we have a carry, we need to consider this OR gate with its inverted inputs. Now, if now the bottom input of this OR is the generate signal, and if that is on, well then this OR outputs true. And again, we already knew that we were in the propagate or generate state. Well, now we know which of the two states it is, the generate state, and so we output a carry, and that's irrespective of the carry input to this bit. Right? I can toggle this as much as I want. It's not going to change. Of course, pay attention to this line after the inverter, because that's more intuitively understandable. So anyways, so the generate line takes precedence over the carry input. But if we are not in the generate state, so I'll disable one of these now, one of the summoned bits, well then whether we have an output carry depends on the input carry. So right now we have no input carry, so there is no output carry. If I switch the input carry on, well now we have an input carry that is propagated to the output carry. So down here because we are not in the generate state up here, we know that down here we're in the propagate state, and there's an input carry which unsurprisingly gets propagated to the output. Okay. So much for the even bits. Now, I'll switch the input carry off here so that we don't have a carry output either, and now let's look at the odd numbered bits. So, once again, so this time it's the other way around. This time we have an OR gate at the end that's being fed by an AND gate into one input. Once again, we'll look at this in reverse. So first we look at this ending OR gate, and the bottom input of that is the generate signal. And if that, if that is on, so if if these two summand bits are both on, well then the generate signal is on. And well then that once again overrides anything else. So if the generate signal is on, we don't need to care about this AND signal over here, because we already know there's going to be a carry output. If, however, the generate signal is off, well then we need to consider the AND statement here instead, because that could power this, that could cause this OR gate then to output 1. So once again we look at the bottom input first, and that's the PG line. Right now it's off, so that means we're in the kill state. So that then means we don't even care about the input carry, because, well, if we're in the kill state, there's never going to be a carry out, right? So I can actually demonstrate this. I will toggle the input carry, and as you can see right now we're in the kill state here, and that takes precedence over the input carry. I can toggle this as much as I want, it's not gonna change the output carry. Alright, but if we are not in the kill state here, well then we are in the propagate or generate state, but because we already know, because we only care about this part if we are not in the generate state, well that means we know that we must be in the propagate state. And so just like before, the carry input into this bit now determines what the output carry will be. So right now the input carry is off. If I toggle the carry into bit 0, that will also toggle the carry into bit 1, and so now we are in the propagate state and there is an input carry, so there's also an output carry. So once again, if you look at this line, there it just gets propagated to the output. And of course then, because it then has to go into another even numbered bit, it has to be inverted once more at the very end. Hence also why this has the slash in front of it, because this is an inverted line. But we're probing it before we do that. Alright. So and then of course these two components, so this component pair here is present 3 more times for the remaining 6 bits of the ALU. Okay, if I have said anything wrong, please feel free to correct me in the comments. This is a learning experience for me as much as you. If you have any other criticism, please also let me know. Lastly, if you have any questions, please also feel free to ask them in the comments. I am looking forward to your responses. Goodbye.